If you have been studying pKa's and pKa's of organic compounds for some time, you might start to wonder, why the heck do we care about pKa's? And it's really important to understand that acid-base reactions are extremely important in all of life and many of the non-life related chemical reactions. And so acidity is a really important concept to understand if you want to understand the course of some reactions. So I've got an equation here, written totally old school with an equal sign between the reactant, potential reactants, and the potential products. And if we understand acidity of the acids here, and thus the basicity of the conjugate bases, then we have a shot at understanding whether this reaction would go forward or not. So if HF is a reactive enough acid, and acetate is a reactive enough base, then they will react and form these products, acetic acid and sodium fluoride. If these are not reactive, then they won't react. They'll just sit there and do nothing, and that would tell us that if we mixed these two, they would react and form the so-called reactants as products of the reverse reaction. So the language of this is that a reaction is either going to be reactant favored, meaning nothing will happen if these reactants were mixed, but if those so-called products were mixed, the reaction would go this way and form the reactants, or it would be product favored, meaning if these two were put together, they would react and go forward and make those products, and if you put those products together, nothing would happen. So there's a fundamentally more stable pair, and when those things form, then nothing would happen. And they'll often draw this as equilibrium arrows in the modern day, rather than the equal sign, meaning the reaction could either go forwards or backwards, depending on the relative reactivity of the reactants and products. Alright, so a couple of statements that pop to mind when I think about acid-base reactions is the equilibrium favors the formation of the weaker acid and the weaker base. So we're looking for the weaker acid, which will be the one with the higher pKa. So that's a really important thing. If we look at the acids on both sides of the reaction, the acid with the higher pKa is going to be the more stable one, and if that could form, it's going to form. If you already have that, it's stable and won't react. So if we could slap pKa values on HF and acetic acid, hydrofluoric and acetic acids, we'll know right away whether this is going to favor the reactants or the products. Another important statement is, in a salt, the anion is generally a base. So you may know a little bit about bases, like hydroxide is a base or ammonia is a base, but anytime that you have a salt, like here we have sodium acetate, the acetate part, the anion part, being negatively charged, might want to go grab an H+, and that would make the acetate anion a base. And so that's often the case. I wish this were emphasized more in general chemistry classes, that almost all anions are bases, but if they didn't, then I'm telling you now. Most anions are bases. Some are stronger than others, but they generally are capable, if they're negatively charged, of attracting an H+, and that would make them bases. This again, something that I mentioned before, and I'll keep mentioning. The lower the pKa value, the stronger the acid is going to be. So if you have a pKa that's negative, you've got a very, very strong acid. If your pKa is up in the 40 to 50 range, it's not generally going to be an acid at all, and it might take an extremely powerful base to pull an H+ off of something with a very high pKa. And here's something that I think is really important when you're starting to work in the world and look at compounds you may not have seen before. If you don't know the pKa of a compound, you can compare to reference compounds you do know. So if you have an alcohol, like methanol, CH3OH, right, that is going to be very similar pKa to a lot of other alcohols which all have this little piece of functional group, a carbon attached to an oxygen attached to a hydrogen. If these other parts of the molecule, hydrogens, are very similar to methyls or ethyls in terms of how they would affect the reactivity, so methanol, ethanol, propanol, butanol all have very similar pKa's and very similar acidities. So that's one of the useful things about identifying functional groups and properties of different parts of a molecule, is they will help you to make predictions about the reactivity of those molecules. And then the strength of the acid is related to the stability of the conjugate base, is something we especially talked about when we're looking at resonance effects, that something like acetate often has a very stable conjugate base relative to other bases like methoxide, because there's stability in spreading out the negative charge. So this is something that there's an inverse relationship that's often useful to think about when you're trying to evaluate the strength of an acid. A lot of times it's valuable to look at the strength of the conjugate base or the stability of the conjugate base to evaluate that. Alright, so there's a couple of pieces I'd like to add to this beyond these statements, and I'd like to sort of put it in action. So if we have HF, I'm going to go full Lewis structure on this one so that I can study the mechanism of how this reaction would go. And then we throw it in with acetate. Don't want to violate the octet rule over here in the video. Get caught for life. Alright, so hydrofluoric acid plus, and I just did acetic acid sort of out of habit, but what the molecule that was here was the sodium acetate, not acetic acid. So going back to what was written on the page, hydrofluoric acid, right there, sodium acetate. The acetate does not share electrons with the sodium is the way we look at it. So I draw two independent dot structures, one for the acetate and one for the sodium. Now the acetate is going to be a base, and the hydrofluoric acid is potentially an acid, right? And so that may or may not react to form the acetic acid. And if I didn't know what the products were, so a lot of times they'll just give you a couple reactants and they'll say, draw the potential products. And this is where the understanding of the mechanisms of reactions is going to be super, super important. So the way most bases work is they have a lone pair of electrons, and that lone pair of electrons is going to go and grab the H plus off of the acid. So what I'm indicating here is that this pair of electrons is going to go and grab the H plus off the acid, and that'll form the OH bond. And then what used to be bonding electrons in the HF are now going to convert to lone pairs, a lone pair of electrons. So I'm using arrows to show the change in function of the different electron pairs, that this lone pair of electrons is going to turn into a bonding pair as it grabs this H+, and then this bonding pair, as it leaves the H alone, is going to become a lone pair on the fluorine. And so when I execute that transformation, I'm going to get the structures. We get the structures of the acid and the base that are potential products. So as I was writing it out, I have the CH3, and a lot of this won't change, right? So the CH3 and the C double bond O in the acetate are not going to be affected here, and the oxygen has two lone pairs, but now the third lone pair is now the thing that's grabbing the H+, as I put it there, and that'll make your acetic acid. So you can see the base grabbing the H plus makes the acid, and that would be called the conjugate acid. So the base picks up an H plus to become the conjugate acid, and then in the HF, the bonding pair that used to, bonding pair of electrons, that used to attach the hydrogen to the fluorine is now going to go just to the fluorine. That's why I wrote it here in red. The new lone pair of electrons, and so now fluoride, being an anion, that could potentially be a base, and that's the conjugate base of the HF. Right, so if you follow the mechanism, and this is something that during the semester I end up saying dozens of times, is that the way acid-base reactions usually go is a lone pair on the base goes and grabs the H plus off the acid, then the shared pair of electrons between the hydrogen and the rest of the acid, so this bonding pair becomes a lone pair. And if you just follow and execute those changes, you get the structure of the conjugate acid, which is the base plus the H plus, and the structure of the conjugate base, which is the acid minus the H plus. So this transfer of the hydrogen ion, we sort of show how it works like this. Now in predicting, is this reaction going to happen or not, we're going to look at the acids. So acids have pKa's. And if something's potentially going to act as an acid, we're going to want to evaluate its pKa. So acetic acid is a classic. pKa equals 4.74. And hydrofluoric acid, a little less well known. Most people don't work with it because it's pretty toxic. It will react with glass, and so it's sort of hard to store and work with. Its fumes are very toxic to us. Its pKa is about 3.2, so it's not its great acidity that makes it so dangerous, but its other properties in the molecule. But now if I look at the pKa's, the pKa of 3.2 means this is the more reactive or stronger acid, and pKa of 4.74 means relative to this one, that's the weaker, more stable acid. So in evaluating the strengths of the acids, we find that the products are more stable. So the more stable acid is in the products, so this reaction is going to be product favored, and the reaction will proceed. So if you mixed HF, hydrofluoric acid, with sodium acetate, there would be a very vigorous reaction to form the acetic acid plus the fluoride. And we can see that by looking at the pKa values. So the stronger acid is going to push the reaction forward in this case, and you're going to end up generating the weaker acid, which is a more stable compound, and thus a nice product. So here's an example of an acid-base reaction, how I can use pKa values to predict whether the reaction goes forward or not. So the reaction happens, to form product, so we're going to say it's going to go forward, and by looking at the mechanism of how the hydrogen ion moves, what grabs the hydrogen ion and what's the resulting leftover after the hydrogen ion leaves, in that way we could predict the products. So the hydrofluoric acid reacts with sodium acetate successfully to form acetic acid and fluoride. Super cool.